Large dense crowds show aggregate behavior with reduced individual freedom of movement. In this video, we present a novel, scalable approach for simulating such crowds, using a dual representation both as discrete agents and as a single continuous system. We replace per-agent planning with a continuum-based model that can capture both the large-scale motion of the crowd and individual agents' motions. We treat the crowd's motion as an aggregate flow and introduce a novel variational constraint called unilateral incompressibility to model its large-scale behavior. This approach greatly reduces the per-agent cost of local planning, making it possible to simulate very large crowds at interactive rates. It adapts smoothly with varying crowd density to provide both collision-free motion in dense scenarios and individual freedom of movement in sparse crowds. Our model efficiently simulates many emergent features of crowd motion. Here we show an example of an evacuation scenario with 2,000 agents exiting a building. We can reproduce the arching behavior of the crowd at flow bottlenecks. Only a limited flow is possible through the exits, and our novel constraint of unilateral incompressibility causes agents to pile up behind each other. Without this constraint, a naive inter-agent collision response model would not be able to prevent collisions in dense regions, such as at the doorway. As a comparison, we also show the most recent per-agent model, the RVO method, which performs exact inter-agent avoidance, but at a significantly higher computational cost. While our method models the aggregate dynamics of dense crowds, it places no restrictions on the number of unique goals in the simulation. Here we show an illustrative example where 10,000 individual agents in a circle attempt to walk to the diametrically opposite points. Despite the congestion, no collisions occur and the agents eventually make their way to each of their goals. In contrast to prior work, the heterogeneity of agent goals does not increase the cost of the simulation. It has been observed that crowds exhibit qualitatively different behavior depending on the density of agents. Our hybrid crowd system can easily capture such kinds of behavior. In sparse crowds, agents can move freely without much inter-agent interaction. As the density increases, a changing pattern of lanes and vortices forms automatically in the crowd, allowing the agents to move past each other. Eventually, when the density is too high, the motion becomes significantly congested. Our method can be easily combined with other per-agent planning techniques. Here we show a group of our continuum-based agents on the left interacting with a group of RVO-driven agents on the right. As a realistic demonstration, we simulated a large trade show with 80,000 heterogeneous agents. Initially, each of the 80,000 agents has a random goal which is updated whenever reached, emulating a random browsing behavior. Later, an evacuation begins, and agents move to the nearest exit, which causes congestion and a gradual outflow. Here we show 100,000 pilgrims moving in 4 different directions in an outdoor scene. We designed this scenario to emulate the plane of Arafat campsite in the route of the Hajj pilgrimage. We can compare this to footage of the actual real-life scene. From a closer view of the simulated crowd, it can be seen that our results exhibit qualitatively comparable and plausible behavior. We also simulated the motion of pilgrims in the Al-Masjid al-Haram in Mecca. In our scene, there are 25,000 agents, of which half want to circle the central Kaaba and half want to move out of the scene. The interaction of these groups forms a complex flow. Again, there is a large number of agents at a high density, but the agents do not collide and the motion of the crowd is smooth. In conclusion, we have presented a novel approach for simulating the aggregate large-scale dynamics of dense crowds that scales well with the number of agents. Using a hybrid model, our technique combines continuum-based and per-agent approaches and adapts seamlessly to variable densities of inter-agent interactions. Thus, we are able to achieve interactive simulations for very large, dense crowds consisting of up to 100,000 agents.